Hello everyone. Today I will talk about plasma assisting green ammonia production from water and nitrogen at atmospheric pressure plasma. So this work has been done by plasma nitrogen fixation team of Department of Plasma Engineering, Korea Institute of Machinery and Material. We are team members Muhammad Majid, Dr. Khoe, Dr. KIMM and Professor Lee. So first of all, I will talk about carbon dioxide related issues and their solution. Then I will introduce low current arc configuration and our reactor system. Then we will talk about two different ammonia production pathways from plasma. So first of all, we all are having issues like global warming, our dependence on fossil fuel, and high energy demands. Actually, all these three issues are correlated with each other, and there is a one common keyword in all these three issues, that is carbon dioxide emission. So due to high energy demands, we need to depend on fossil fuel, and with fossil fuel combustion process, CO2 emission is there that produce greenhouse effect, and that is responsible for global warming. So about carbon dioxide in next slides I will talk. So to tackle these issues, there is solution of renewable energy, but renewable energy has its own problems, like transportation of renewable energy and storage of renewable energy. So if we utilize that renewable energy to make plasma, so we can convert basic compound into high energy compounds. And in this way, we can store our extra renewable energy, and we can also transport in the form of these compounds. So the question is, where from this CO2 come? So around 73% of CO2 emission is from energy. That energy sector include the electricity from industry, transportation, and energy used in buildings. So there are two strategies to avoid CO2 emission. One strategy is if we can avoid combustion process. So that is the use of carbon-free fuel, or the other is to utilize renewable energy for electrification of compounds. Other way is if we cannot avoid CO2 emission from combustion process, then we need to capture CO2 and then we will convert that CO2 with the help of plasma into other valuable compounds like plastic, fuel, and other chemical compounds. In this work today, I will introduce about carbon-free fuel and electrification from renewable energy. So if we talk about carbon-free fuel, there are two type of carbon-free fuel. One is ammonia and the second one is hydrogen. So we will discuss about ammonia because ammonia has 2 times higher density as compared to liquid hydrogen. And it is easy to ship and easy to store and easy to burn. Also, we can convert that ammonia into hydrogen if required. So let's talk about plasma. Basically, we have two type of plasma. One is low temperature plasma, or also called partially ionized plasma. In low temperature plasma, electronic temperature is very high as compared to gas temperature. So we can say that gas temperature and electronic temperature are not in equilibrium. That's why we call it non-equilibrium plasma or cold plasma. In high temperature plasma or fully ionized plasma, electronic temperature and gas temperature are in equilibrium. That's why we call it equilibrium or thermal plasma. There is another type of plasma that is gliding arc plasma. We also call it warm plasma because in this case, gas temperature is not at room temperature and also not equivalent to electronic temperature, but it is between electronic temperature and room temperature. So that temperature we can utilize to change different chemical compounds. So here are examples of low temperature plasma like DBT plasma, corona, and spark discharge, and rotating arc plasma and gliding arc plasma is example of warm plasma. RF plasma, ICP system is thermal plasma, microwave and thermal arc with DC high current arc is also example of thermal plasma. So what is difference between rotating arc and thermal arc? In rotating arc, the current level is around 100 amperes. So if high current condition is there, so we call it thermal plasma. But if we talk about less than 20 ampere or around 20 ampere current, then it is called rotating arc or warm plasma. So first of all, we will discuss about famous classical gliding arc. So in classical gliding arc, we have two diverging electrode. And when we apply high potential between two electrode, arc generate between shortest distance, and with the flow of gas, it glide on surface of electrode. The problem with this type of gliding arc system is due to its 2D geometry, there is less interaction of plasma with gases. So in this way, we can get low conversion of gases. So our group introduced state-of-the-art rotating arc plasma. In this reactor, we supply gases in swirling flow. And arc, from here we can see that arc cover all the reactor parts, so all the gases pass through reactor arc. In this way, we have high interaction of plasma and gases. So this video is from high-speed camera inside of rotating arc reactor, so we can see that how this reactor arc rotate inside reactor. There are two type of reactor rotating gliding arc. The one is that is called conventional reactor. In this, we have a high voltage and ground electrode. With the high voltage electrode, arc generate at different points of ground reactor. So we can see that plasma arc generate at different points with different arc length. That's why from here, from IV curve, we can see that different arc lengths are there. So here we can see that with nozzle, if we introduce nozzle type of reactor, arc always generate between high voltage and the nozzle structure. So, and arc is very focused in nozzle-like structure. So here we can see that IV curve is very stable and we can get stable discharge. So let's talk about nitrogen fixation work in our institute. We work on air to ammonia production and air to NOx production and then NOx to nitrate production. There are basically two different ways to change basic compound into ammonia by using plasma. So first way is if we introduce water inside nitrogen discharge, we can get NOx and hydrogen. That NOx can be reduced with hydrogen to form ammonia. In this way, we can get 100% selectivity of ammonia. Another path is if we introduce discharge in air, we can get NO and NO2. And if we further oxidize these NOx with ozone, we can change into N2O5 that dissolve in water to form nitrates. And these nitrates, with the help of electrochemical process, we can change into ammonia. So let's discuss in detail about first part. We introduced plasma nitrogen discharge in water, and we got hydroxyl radical, oxygen radical, and nitrogen radical. From hydroxyl radical, we got hydrogen, and from nitrogen and oxygen, we got NOx. And the hydrogen we got is oxygen free. So the expectation is that from water splitting equation, we always get hydrogen and oxygen. So in next slides, we will discuss how oxygen disappear. So the NOx, some of NOx dissolve inside water to form nitrates, and other NOx react with hydrogen in the presence of palladium catalyst to form ammonia. So these processes are fully electrified and does not involve Haber-Bosch process, and it's a single step to generate hydrogen and NOx together, and its work at atmospheric pressure, and fast switching is also its advantage. So let's talk about its configuration. So in plasma system, we introduce nitrogen discharge and water, and then it forms NOx and hydrogen. One part of NOx dissolve in water to form nitrate, and other part of NOx react with hydrogen to form ammonia. So here is our reactor system. We can see that this one is high voltage electrode, and we introduce nitrogen from here in swelling flow, and we introduce water from here in the form of water film. So the question is why we introduce water in the form of film. Actually, problem with the water is due to its conductivity, it always disturb the discharge condition. That's why we introduce water in the form of film, so that at the it less interaction at the start of arc. So after that, in the nozzle area, it interact with the discharge, and we can get hydrogen and NOx. And these NOx reduce with in the presence of palladium catalyst, and we get ammonia. So this FTIR connected, one part is directly connected with reactor, and the other part is connected through catalyst. So if we want to check NOx concentration, we will use this valve. And if we want to check ammonia concentration, we will check this line. And GC is also connected to check concentration of hydrogen, oxygen, and nitrogen. So here we can see that when we introduce water in nitrogen discharge, as specific energy increase, production of hydrogen also increase. But unexpectedly, firstly oxygen concentration increase, but after that it becomes zero. Our expectation was like water splitting equation, it should be oxygen should be half of the hydrogen production, but it was zero. So to check where that oxygen is going, we checked with FTIR, and we found that this oxygen react with nitrogen to form NOx. And we can see that as oxygen concentration decrease, NOx concentration increase. So it means all the oxygen is reacting with nitrogen to form NOx. And we get around 98% selectivity of NO. So from here we can see that at low specific energy, the production of hydrogen and production of NOx is almost equal. But as specific energy increase, production of hydrogen increase, but NOx concentration not increase. So that is a good point, because for the production of ammonia, we need 2 molecules of NOx and 5 molecules of hydrogen to make 2 molecules of ammonia. So we can say that we need 2.5 times high hydrogen as compared to NOx. So we divided in this graph into two regions. One is when hydrogen concentration is less than 2.5 times, and the other is when hydrogen concentration is enough for ammonia production. So in next slide, we will see that what will happen if we introduce catalyst in hydrogen deficient region and hydrogen sufficient region. So here we can see that when we introduce catalyst, there is zero production of ammonia, but we got another compound that is N2O. As specific energy increase, N2O production also increase until hydrogen becomes sufficient. After that, all the NOx react with the hydrogen to form ammonia, and production of N2O become zero. Anyway, production of N2O in our system is not good news. So for that hydrogen deficient region, we need to provide additional hydrogen. So when we provided additional hydrogen, we can see that there is no production of N2O, and we can see that ammonia production from the start. These results we also verify with FTIR with real-time results. So from here we can see that when we turn on plasma, we got higher production of NOx up to 0.9%. So after 15 minutes, we turn on catalyst part. When we turned on catalyst part, at start we got small amount of N2O, and in few minutes production of N2O become also zero and ammonia production start. And it was continue. We checked this up to 80 minutes, and ammonia production is very uniform. As previously discussed, some part of NOx react with the hydrogen to form ammonia, and other part dissolve in water to form nitrates, and that is also called plasma activated water, or it is also used as a fertilizer. So it's a kind of bonus. We are getting two different products with one single reaction. That reactor, one is ammonia and the second one is plasma activated water. So let's talk about reaction mechanism. So after that, we open our reactor system and to check optical spectrum with optical emission spectroscopy. So here is a spectrum. We can see that oxygen, hydrogen, nitrogen, NH, OH, and NO radical. So on the basis of these peak, we design reaction mechanism. We can see that production of different radical at different specific energies. So let's talk about second part. We introduce plasma in air, and we got oxygen and nitrogen radical. These oxygen and nitrogen radical react together to form NOx. These NOx further oxidize to form N2O, and that N2O5 react with water to form nitrate, and with electrochemical process we convert these nitrates into ammonia. So these also have similar advantages that it is fully electrified, does not involve Haber-Bosch process, and we can get high concentration of NOx, and it works at atmospheric pressure and fast switching. So reactor system is very similar to our previous system. The only difference is in this work we only supply air and we didn't supply water. And we got high concentration of NOx that we check with FTIR and gas analyzer. Here is our reactor system with power supply. So in this work, we get high NOx selectivity up to 95% with low energy cost, that is around 48 gigajoule per ton nitrogen. So we can say that our energy cost is very near to Haber-Bosch process. But the problem with this system is if we use low specific energy, we can get high energy efficiency, but we also get low concentration. That is not feasible for industrial process. But if we use high specific energy, production become high and energy losses will be also be high and energy cost will be high. So question is, at low specific energy, why we are getting low energy cost? So to answer this question, we have tried three different methods. First one is we check temperature, and when we increase flow rate, or we can say that when we decrease specific energy, gas temperature also decrease. And after that, we check heat losses to electrode and reactor body by checking temperature of cooling water. And we found that at high specific energy, heat losses to reactors are high, and as specific energy become lower, heat losses are also become lower. That's why we get high energy efficiency at low specific energy. To further prove it, we check our reactor with IR camera. So here are front view of our reactor with IR camera and side view. So we can see that at low flow rate and high specific energy, our reactor system is red hot, showing the high energy losses to reactor. But as we increase flow rate and decrease specific energy, we can see that temperature of reactor become almost room temperature. So we can say that when we decrease specific energy, quenching of reaction become very quick and energy loss becomes zero, or energy losses become less. That's why we get high energy efficiency. So this we can also see from the jet area. When high specific energy and low flow rate, reaction volume is high, and when high flow rate and low specific energy, reaction volume is low and reaction is quickly quenched. In this way, we can get high energy efficiency. And we also try to prove this with simulation. So we simulate artificial heat source in our reactor system, and we supply gases at different flow rate with the same power. And we found that when flow rate is low, reaction volume is high, and when flow rate is high, reaction volume become lower, and in this way reaction quickly quenched and heat losses are less. That's why we get high energy efficiency. So we already explained that with the help of rotating arc we can get high concentration of NOx, but if we try to dissolve these NOx inside water, some of NOx dissolve inside water to form nitrates, and other we get from exhaust gas that we check with FTIR. So when we only use arc reactor with water to make nitrate, we can see that we got low concentration of nitrate and high energy cost. And also disadvantage is emission of NOx in air. So to overcome this issue, we introduced DVD discharge to make ozone. That ozone react with NOx to form N2O5. That N2O5 is water soluble, and when it dissolves in water, it forms nitrates. And we can see that after introducing ozone generator, concentration of nitrates become higher and energy cost become lower. And the good news was there was no emission of NOx or ozone that we confirm from FTIR and ozone monitor. So in this way, we introduce a novel route to produce green ammonia. That is, if we produce NOx from air and ozone from DBT reactor, and this ozone react with NOx to form N2O5, and we already talked that N2O5 is water soluble to form nitrates, and these nitrates, with the help of electrochemical process, we can change into ammonia. So conclusion of our work is we introduce novel concept of plasma catalyst integration process to produce ammonia that is very flexible as we can work with renewable energy. And another important thing is we produce around 300 to 400 times higher production of ammonia as compared to all the previous work related to plasma and electrolysis process. I would like to thank all the group members of Plasma Department of Korea Institute of Machinery and Material. If you have any question on comments, or if you want to learn more about our work, you can scan this QR code. Thank you very much, everyone.